Okay. So they call chapter 5 chemical accounting. So basically, we're talking about a lot of things we've seen before. So usually in one in not one in usually in 108, this class in 109, we don't really cover chemical reactions much in the lab. We talk about them and we see them, but we don't really balance them or do anything like that. But we've already had that experience in the lab, balancing equations and doing things like that. So a lot of this should be review, but we're going to get into it. So what is a chemical equation or a chemical reaction? Now, we use it to represent what's any of these chemical changes that we're talking about. So these chemical changes, as opposed to physical changes, we are changing the chemical compound. Really, we're what we call rearranging the atoms to make new structures and to chemically change things. So some examples of those chemical reactions are if you burn something, if you oxidize something, rusting was a form of oxidation, tarnishing silver, things like that are the main ones that we talked about in this class. So we're going to be exploring these equations and what they actually mean, not only on the molecular level, meaning one atom switches with another atom to make a new compound, but on the macro level, meaning this concept of the mole and what that means in terms of our weighing out of tangible scaled up versions of these chemical reactions. So we've seen chemical reactions before where the left side of the equation or the arrow means the reactants. So it's we call them species, but really just think of the molecules or the compounds that are present before the reaction. And they have to add together, or if it's one reactant, it can break down to make one or more products. And then the products are the species or the compounds on the right of the arrow. And the arrow means yields, or I like yields is all right, but I like reacts to produce. So the way I read a chemical reaction is, here's an example of one. So you have 2 molecules of H2 react with 1 molecule of O2, and they react to produce 2 molecules of H2O. That's the way you should be thinking about these chemical reactions. And these coefficients we'll talk about in a second, and you've seen those in balancing equations. But we're also going to be talking about what this equation means on the macro scale. So we'll get into moles in a bit. Any questions on that so far? No? Okay, pretty much review. All right. So there's something else in a chemical reaction which sometimes you may see and sometimes you may not. But it's even if when you do see it, I mean, in the textbook, it's there. And in some chemical reactions that are written in a standard way do have these symbols. So next to the compound, they have parenthesis, either S, L, G, or AQ. Now, if we're doing a reaction of water, we're going to have it in AQ. But what these mean, these just tell us the physical state of the compound or molecule in the reaction. So they're not to be confused with any type of element or anything. It's not something that you need to balance in the equation. It's just the physical state. So it doesn't affect the way you read the equation at all. It's just the physical state. And it's there in some equations. In some equations, it's not. So don't be thrown off by that. S means solid, L means liquid, G means gas, and AQ means aqueous. So we didn't really go into crazy detail about solutions yet, and we will in later chapters. But what aqueous means is that the compound or mixture is in a water-based medium. So we talked about a little bit about polar when it came to chromatography. Maybe you've heard that word thrown around a little bit, but basically in a polar solution where you have different kinds of salts, different kinds of acids, maybe bases, things like that occur in an aqueous solution. So when it's water-based, it means aqueous. Okay, so another thing in a chemical reaction, other than knowing the reactants in the products, the solid, liquid, gas, little parenthesis, physical state, is the coefficients. So we should be pretty familiar from the lab about the coefficients. Now, these coefficients tell us the number of molecules that are required of each reactant or product to make the left and right side balanced. So we know what balancing is, but just to reiterate, you can't have a different number of hydrogen atoms on the left side of the equation than you do on the right side of the equation. So if we look at this non-balanced equation, where we're adding hydrogen gas and oxygen gas to create water, you have H2. So you're having 2 hydrogen atoms reacting with 2 oxygen atoms to make 1 molecule of H2O. There's a problem there. The problem, well, who could tell me the problem?
They didn't add O2.
Good job, Kaylee. Good. So O2 is the problem because on the right side, you only have 1 oxygen. On the left side, you have 2 oxygen. So where did that extra oxygen go? You can't just disappear because we consider this to be a closed system and it would violate the conservation of mass. It disappeared. So what we have to do is we have to put these coefficients in front of our molecules or compounds to account for this, to balance this out. And there's certain ways to do it. And you see these 2 X's where things you can't do is you can't change the chemical equation, meaning you can't add anything else to it. You can't subtract anything. You can't change the subscripts either. So if you change the subscript, if you make H2O, H2O2, and you drink it, you're going to die because it's hydrogen peroxide. So changing these equations will be drastically different in this way, where you put a subscript or you add another atom, which is not the way to do it. But the way to do it is to multiply. So multiply using the coefficients and putting those coefficients in front of the molecule or the compound to make them equal. So there's a certain way to do that, and we'll talk about that now. So we'll go through this one right now on how we got to that 2 and 2 answer. So I'll get my pen out. Okay, so just to review this again, like we did during lab, the way we balance equations, the easy way to do it in this class is we're just going to read the reaction just like we do a book, from left to right. And we're going to see how many atoms of each element are on the left, compare that to the right, and then go through the equation in that way. So let's do that. So we have H2. On the right side, we have H2. So right now, hydrogens are good. Then we have our problem, which is O2 here on the left. And then you have just 1 oxygen here. So to make that equal, you have to put a 2 in front of the H2O. Now this changes the number of hydrogens. So now how many hydrogens do we have? 2 times the H2, which is 4. So then 4, we need to make this H2 equal to make it 4 hydrogens. So we can put a 2 in the front. And then we're all done. And then you can always go back and check it out, check it over. You have 2H2, which is 4 hydrogens, 2H2O, that's 4 hydrogens, O2, 2H2O. So that's going to be 2 oxygens. So that's a completely balanced reaction. So this is going to be how we're doing it. Any questions on that? No? All right. So we're going to be doing some examples now. Here's just the same equation. Yeah. All right. So here's what we're going to do. We'll do the first one together, and then I'm going to give you maybe 3 or 4 minutes to do the next 2. All right. So the first one, we have S8. We have sulfur 8. And we have plus O2 reacts to produce SO2. So we have, well, first of all, quick question. What's the name of SO2? Based on our naming that we learned about.
Sulfur dioxide.
Perfect. Good job. So now S8, we have 8 of them here. Go look over to the right. We have just 1 S. So we should put an 8. Okay. So now sulfurs are good. Now for oxygen. Oxygen, we have O2. Now, since we put this 8 there, the 8 kind of like algebra gets distributed into the sulfur and the oxygen. So how many oxygens we have now?
16.
Good. Awesome. So we have 16 oxygens. Now to make O2 equal 16, we can put an 8, just like we did for there, but for different reasons. Well, it makes it work. So yeah, this, and if we don't have a coefficient, we can consider that to be a 1. So that would be the balanced reaction, and you can check it over. You have 8 times 2 oxygens, 8 times 2 oxygens, 1 times 8 sulfurs, 8 times 1 sulfurs, and that works out. Okay, so any questions on that one? No? Good job. You guys are on the ball today. So for the next, let's see, it's 8:13 now. I'll give you till like 817 to balance these next two, and then we'll go over them together. I'll give you one more minute. All right, let's start taking a look at the first one. So this one's a little different, but same concept. All right, so there's something first. It's always good to read the equation first to kind of get a plan of attack for how you're gonna balance it. Now you notice something. There is this NaNO3, right? And we've seen NO3 before. When we learned how to do naming, we talked about ionic bonds and we talked about the polyatomic ions. So NO3 is nitrate. It's one of those polyatomic ions. Even if you don't remember the name of it, the charge of it, you should still definitely recognize it. And sulfate is one of them too. It's common carbonate. You should recognize them if they occur on the left and the right side of the equation. And in this case, they do. So you have the nitrate here is the NO3, and then here's the NO3 2, meaning you have two of these NO3s on the right side. So it's really good to recognize those polyatomics because it'll make your life a lot easier. Even if you don't recognize them, you could still easily balance the equation, but it will be harder to do than if you did recognize them. So let's go through this. And the reason why we're recognizing them is because we're not going to just balance the nitrogens, the oxygens within the nitrate, because we're going to balance the nitrates as their own entity. That's a lot easier to do when you have nitrates on the left and the right side. So, for example, let's say you were going through this without looking at the nitrate. I'll show you what will happen. Is you do sodium, you get 1. Sodium, there's 2. You put a 2 there. Nitrogen might be simple also because there's 2 places of nitrogen. But when you get to oxygen, here's what will happen. You'll have, in this case, you'll have 6 oxygens here, and then you'll have a 7th one from the PBO. You'll be comparing that to the 6 and the 7 over here. In this case, it does work out, but in some cases, you might have different number of oxygens coming from different sources. That's where balancing can get really complicated. So for polyatomic ions and for things that are ionic bonds, it's easy to simplify your work by doing that. All right, so let's go through this. So we have Na, and there's Na2, so we're going to put a 2 right there. NO3, there's one NO3 here, or sorry, there's two NO3s here. Now that we put this 2, and then there's NO3 too. So that's all good. Then we look over to PB. There's PB, there's PB. We're good there too. Then we have oxygen. We have one oxygen here for the anion oxygen, the oxide. And we have one oxygen here. Maybe I should have picked a harder one, but we're basically done. So just putting that 2 there kind of solves it for us. And yeah, it's a pretty easy balancing. Yeah, cool. All right, next one. So we have Fe, and then we have Fe. So we're good there. Ag, we have Ag, so we're good there. Now NO3, so more nitrate, right? So we're going to balance the entire entity of NO3. So we have NO3, 2. So we have to put a 2 right here. Now that changes the number of silvers of Ag. So now we have 2 Ag, so we have to put 2 Ag over here on the right side. And that balances the equation. And everything else is 1. So yeah, so these are kind of more basic balancing equations. They do get a little bit more difficult, or actually they do get a lot more difficult. But in this class, we'll only get to a certain difficulty level. So there is one other type that I want to do, which I think you did see during the lecture, which was combustion, or during the lab, which was combustion. So combustion, let's do an example. Let's do C2H6 plus O2 yields H2O plus CO2. So for this one, we do the same thing, but you encounter a little bit different scenario. So let's do C2, you have 2. CO2, you have 1. Let's change the color. So we're going to put a 2 right there. Then for H6, so H6, you have 6 of them. For H2O, you have 2. So what are we going to put in front of the H2O?
A 3.
Perfect. 3. Good. So now what do we have? The only thing left to balance is oxygen. Now the oxygen's on the right side of the equation. We have 3, and then we have plus 4. So we have 7. So we have 7 oxygens on the right side, and we want to make the left side of this balanced, where the left side just has O2. Now, if we put a 3 here, that would give us 6 oxygens, not quite 7. So what we can do is we can cheat a little bit. Instead of putting 3, we can put 3.5. Because doesn't 3.5 times 2 equal 7? Yeah, it does. So we can put 3.5. And does everybody understand? Or another way we could write it is 7 over 2. Because we get that 7, it would be just 7 over 2. Now, does that make sense? If not, ask questions, because that's a difficult thing for some people.
Can you repeat that again?
Yes. So what we're going to do, and so the reason why we're doing this is because the right side of the equation has basically an odd number of oxygens, and we're trying to cancel that odd number out with a coefficient in front of an even number. So we have to use a decimal, 3.5 in this case. So 3.5 times 2 would equal 7. And if it's easier for you to think about it that way, you could just write 3.5. There's nothing wrong with that. So 3.5 times 7. Basically, you're asking yourself, what times 2 equals 7? No matter what it is. So just like math, 3.5. Is that better? Good. Okay.
Professor, what kind of problem is this? What's the name for it?
Oh, this is balancing equations.
Oh, no, I'm saying this specific problem.
Oh, combustion.
Okay.
Yeah. Okay, so does everybody understand how I got this far? We're still not done, but we're almost done.
Can you still repeat it again?
Yeah,
Okay.
go over one more time.
Okay, all right. So does everybody understand how there is 7 oxygens on the right at this point? Because we balanced out the carbon and we balanced out the hydrogen.
No.
How did you
not
got 7
sure.
for oxygen?
Okay, so we're going to do it again because I heard a no. So we're going to do it again. And keep in mind, this is as hard as it would get. So if you're a little stuck, that's okay. All right. So C2, right? Let's look at the right side. Where's carbon? Right here. C2 and just C. So we have to put 2 right there. Right? Okay. Next, keep reading it. We have H6. H6 on the left, H2 on the right. So what do we put here in front of the H2O?
3.
Perfect. 3. Nice. So now our carbons are balanced, hydrogens are balanced, oxygen, not yet. So let's look at the right side because oxygen's just alone here. It's just O2. Let's look at the right side, see what we need to put in front of here to make O2 equal to the right side. So we have 3 oxygens because this 3 gets distributed into the H2O. And then you have 2 times CO2, meaning 2 times 2, which is 4. So you have 3 plus 4 equals 7. So we have 7 oxygens on the right side to balance with the left side. Now, we need to put a coefficient in front of O2 to balance out 7. So what times 2, meaning this O2, would equal 7?
3.5.
Exactly. That would be 3.5. So it seems weird to put a decimal in front of a chemical quantity like this, but you can do it for now. So before I continue to the next part, does that make sense now on why we put 3.5?
Yeah.
Yeah.
Okay, good. All right. So now that we have 3.5, we can't, this is not a completely balanced equation, even though the left side does equal the right side. Because if you read this on a molecular level, you can't say 1 molecule of C2H6 combines with 3.5 molecules of O2. That's not right. You can't have 3.5 molecules. But you can have 3.5 moles. We'll go, that's later. But we need to have these coefficients in whole numbers. So they have to be in integer numbers. So any ideas on how we would do that?
Multiply the entire thing by.
Perfect. Perfect. Good job. So you can multiply the entire thing by 2. That would make every coefficient equal a whole number, an integer whole number. So the correct balance equation, I'll write it in green, I'll write it in green up here, would be 2C2H6 plus, since you're multiplying every coefficient by 2, this would now become 7O2 yields 6H2O plus 4 CO2. Ta-da, all done. All right, does that make sense? Good? All right, cool. All right, so that's the basics of these balancing equations, and you will see a couple of these on the exam. So not too many. I'm not going to go crazy with it, but you will see a couple of them. Okay, switching gears a little bit. Now, we understand these chemical equations in a molecular meaning on an atomic scale of you're adding one molecule to another to make other molecules. But we need to bring this up into the macro scale because we can't do experiments on the molecular level because we just can't see them. We can't see all these molecules. We can't weigh out 5 carbon atoms. So we have to use this huge number to kind of scale these up. And this number is called the mole or Avogadro's number. So you can call it avocado's number because I've heard that before. That's funny. So Avogadro's number, very important. So this number will be given to you on the exam. You don't have to memorize it, but when you're doing these calculations, you probably will end up memorizing it because you'll be using it a lot. So it's 6.02 times 10 to the 23rd. That's Avogadro's number. And it's defined, I'll explain this definition, but one of the ways it's defined, it's the number of atoms in a 12-gram sample of carbon-12. So basically, they're using carbon as their standard. And they're saying that, all right, carbon 12, remember that isotope carbon 12, the most common carbon atom, is considered to be 12 grams if it has, it's exactly 12 grams, if it has a Avogadro's number of molecules in that sample. So an Avogadro's number of molecules is what we call a mole. That's what the mole means. So mole. Now, the carbon is just using as a standard. Don't really think about that. But these numbers, this 12 grams, that came from somewhere. So you've probably seen 12 grams for carbon before. And on the periodic table, you see that. So you see carbon as 12.01 to be more specific. But that's when you average out all the isotopes. But if you're just talking about carbon 12, the exact mass of carbon 12 is 12 grams. Or is 1 mole of carbon 12 is 12 grams. So now we're looking, now you see that, all right, we're going into grams now. Now, atoms are very small. If you get 1 or 2 or 5 atoms of carbon 12, you're going to be talking about 10 to the negative 27 grams. Not even 0.000, 27, 26 zeros and a 1. That's how many grams you're talking about when you're talking about just singular atoms. That's nothing. So we have to use a huge number to scale that up. And this huge number is the mole. So we're going to measure our samples of our atoms in real world chemistry. Our samples, we're measuring them using molar amounts and using grams or milligrams or kilograms, but we're scaling them up so we can see them and we can accurately work with them in our hands. So does that make sense of what the mole is? It's just this number of atoms that scales up a certain sample, and it has a specific mass. For carbon, it happens to be 12. For every other element, it's different. Yeah, okay, so we'll do more examples, but let's talk about this number first. So this 12.02 is the mole. So here's the definition of the mole. So the mole is defined as the amount of substance that contains 6.02 times 10 to the 23rd particles. So this doesn't apply to just chemistry. The mole is a number, just like if you say dozen, a dozen eggs, right? That means 12 eggs. A dozen students, that means 12 students. The meaning is the same. So a mole of anything is an Avogadro's number of that thing. But once we go over the comparison of how big this number actually is, you'll see that the only logical thing to count in moles is atoms and molecules, because you'll understand why in a second. So to get to that, so how many of you, so you can write in the chat or you can say it out loud, how many of you think that there is a mole of trees on the earth? So you write yes or no, or say yes or no. So a mole of trees on the planet. So think about all the forests, Caleb, that's a good guess. All the forests, all the jungles, New Jersey has a lot of trees.
No.
It's all right. So we have yes, no. Some people are probably not sure. That's why you're not saying anything. That's totally cool. So the answer is, Caleb changed his answer. So actually, no. So yeah, correct on changing your answer. So there is a lot less trees than 1 mole. So I'm not sure how many trees there are, but it's a lot less than 6 times 10 to the 23rd. Not even close. That's all right. So now how about things like blades of grass? We'll do that one. So blades of grass. So meaning every wheat field, like you go to Africa, it's like the Sahara or the Serengeti, not Sahara. Sahara's a desert. Serengeti of all those wheat grass, all that grass, thousands, millions of miles, millions of square miles. So still no, right? And that's the correct answer. So think about every blade of grass on planet Earth. Every blade of grass. Think about how much land we have. Most of it's grass. There is not even close to a mole of blades of grass on the earth. Think about how big. You can't even contemplate. I can't even think about how big that number is. That's crazy. All right, so now the last one, you can kind of see where this is going. How about grains of sand? Grains of sand. So you think about it, you have grains of sand on the beaches. Sure, there's not that many beaches, but also on the bottoms of the oceans and the deserts. The Sahara Desert and Gobi Desert is like, each one of those is almost the size of the United States. And then you have the bottoms of the oceans, which are 75% of the mass, or 75% of the surface area, and it goes miles deep in terms of sand. So if you were to guess still no, then you're right. Think about that for a second. There's grains of sand, very, very tiny. There's on a beach, there is trillions of them on a beach. Maybe not trillions, maybe billions of them on a beach. On one beach, there's thousands of beaches. There's thousands of lakes where there's sand all over the place. Millions of lakes. There's oceans, under the oceans. There's the deserts that go miles deep in sand. And still, there is not even close to a mole of grains of sand on the earth. So a good question would be, all right, how many grains of sand on the earth are there? And I looked this up because somebody counted them. No, nobody counted them. It's, they did like a surface area study. So approximately, and this changes every day, of course, there is 3 times 10 to the 18th grains of sand on the earth. I'll say per earth. Hold on, my cat is biting. She's tearing apart a box. Whatever. She ran away. Okay. So 3 times 10 to the 18 grains of sand. Now, if you compare that to the mole, there's a lot going on. So if you divide 6 times 10 to the 23rd, we'll ignore the 0.02. 6 times 10 to the 23rd divided by 3 times 10 to the 18th. Let's see what we get. 6 divided by 3 is 2 times 10 to the 23rd divided by 10 to the 18th. For those of you who are math or like math, what's that equal to?
10 to the 5th.
Perfect. You'd subtract the 2 exponents. So 10 to the 5th. So this means 10 to the 5th is a 2, or 2 times 10 to the 5th is 2 and 5 zeros. So that's 200,000. So this means that it doesn't mean that, oh, there's 200,000 more molecules in a mole than there are grains of sand. No, there's 200,000 times more molecules in a mole than grains of sand. 200,000 times. So if you took all the grains of sand on the earth and multiplied them by 2, just 2, that would be enough sand to cover all the land and probably fill up like half the oceans. If you multiply it by 10, the earth is probably encased in sand, probably like a couple of feet deep at least, if you multiply it by 10. If you multiply it by 1,000, we're probably a couple of miles deep, maybe a mile or 2 deep in sand. That's 1,000. 200,000. That's like, I don't even know, maybe like 10 Earths worth of sand. Maybe even more. I'm not even sure. That's a lot of sand. And 200,000 times the grains of sand on Earth is the number of particles that can, of carbon, that can fit in your hand. And they weigh 12 grams, just 12 grams. You wouldn't even realize them if they're in your pocket. You wouldn't even recognize they're there. Things like lead, it would be 200 grams and it'd be kind of heavy. But still, you'd still be able to hold it. That's insane that this number exists. And this number shows us that how small these atoms and molecules are. And how small they are compared to a grain of sand. Not even close. So just to reiterate that, every grain of sand on the earth multiplied by 200,000, crazy number, is the same amount of particles of carbon that can fit in your hand, and it would be 12 grams. And it's the same thing for hydrogen, and it would be 1 gram, and it would fit in your hand. So that's crazy. I hope your mind got blown on at 8:40 a.m. on a Monday. Boom. Now, Kaylee has a question. Good one. So has anyone calculated how many trees on the earth? That's a good question. So Kaylee, for extra credit, you can go and count every tree. That's what you can do. And you'll get, I don't know, 3 points on your next exam. I think that's fair. That's a good thing you can do.
Sure, why not?
Yeah. That's a good question. Maybe you can Google it, and probably they did some kind of surface area study. But since there's wildfires and all that stuff, it probably changes a lot every day. And also, yeah, it's probably going down because like deforestation. But that's kind of really highly regulated now. So hopefully trees are making a comeback. They're important. Okay, so the mole, we talked about that. So this I don't think is true. The first one I don't think is true. A mole of baseballs is not the mass of the earth. I don't think that's true. Because a mole of grains of sand is more than the mass of the earth. So a mole of baseballs would be like insane. But the second one, I had never thought about this one. I think that's true. So a mole of drops of water is equal to the mass of the oceans. Think about that. Drops of water. If you have a mole of them, it's all the oceans. That's insane. I think that's a better example than the grains of sand because you can quantify that. That's still nuts. Okay, so moving on is what we can do from this mole and why we're using it. And I said that already. Is we're using it to scale up these small chemical quantities to masses that we can understand and we can use in our calculations. And we can use. This is called the formula mass, atomic mass, molar mass. In our intensive purposes, they're the same thing. So the atomic mass or the molecular mass is the mass, or is the average atomic mass of a molecule. That's basically what it is, the molecular mass. And how do we figure out these molecular masses? They're very easy to figure out. All you have to do is look at a periodic table. So I will get a periodic table. Periodic table. Where's ptable.com? There it is. Cool. So if you look at a periodic table, everybody should be able to see it, right? Yep. Okay. So look at a periodic table. You have these decimal numbers here, and we talked about these. These are the average atomic masses. So for carbon, the average atomic mass is 12.01. So if you have a mole of carbon, it weighs exactly 12.011 grams. If you have a mole of thallium, it weighs 204 grams. It's getting kind of heavier because they're bigger atoms. But the idea here is that every element, we can tell how many grams per mole that element is based on its atomic mass. So right now, you should be able to figure out the atomic mass of anything if you had a periodic table in front of you. So things like oxygen's 16, fluorine is 19, neon's 20, argon's 39.94. In some cases, you can round. If the number is extremely close to the whole number, you can round, such as carbon is 12.01, you can round to 12. Nitrogen is 14.007, you can round to 14. Oxygen and fluorine, you can round to their whole numbers. Things like boron, I wouldn't advise it because it's 10.8. So it's not close enough to 11 to where you can round it. Chlorine, definitely not because it's in the middle, 35.45. So it wouldn't be advisable to round chlorine to 35 in your calculations. But don't really worry about rounding. Just worry about getting the correct answer in general. If you don't know whether to round or not, be safe and don't round. Okay, so how do we calculate these? Here's some different quantity like carbon, copper, salt. There's a mole of everything. There's a mole of stuff. But let's do some molar mass first. So let's say if we had CO2, right? what would be the molar mass of CO2? We can't only find the molar mass of an atom, we can find it of an entire molecule. So if we look back at the periodic table, we see that carbon is 12.01 and oxygen is 15.99, basically 16. So what we can do is the way to calculate the average atomic mass is you simply add up the elements' masses. So carbon's 12 plus 2 times 16. And 16 is for the oxygen. And there's 2 of them. And this equals 44 grams per mol. That's the unit. Okay. Is there any questions on that? On how I got 44 and what I did?
Can you?
Can you repeat that again?
Sure. So for the molar mass, what you do is to figure out the molar mass of any compound or really any chemical quantity, any formula, is you add up the molar masses of each individual element. That's it. So going back, if you look at the table, carbon is 12, oxygen is 16. So you're going to add up 12 for carbon plus 2 times 16 for the 2 oxygens, and you get 44.
Oh, okay, good.
Okay, cool. And that applies to every single case. So we'll do one more case that's a little bit more difficult. So do Na2 SO. No, we'll do, I don't know. I have a better idea. Here we go. Do Mg NO3 2. All right. So I'll tell you right now, or we can look at the table. So let's look at Mg, nitrogen, and oxygen. So magnesium is right here. So magnesium has a molar mass of 24.305. So we could put 24.3, 24.31. That's acceptable. Fine. Now we look at nitrogen. Nitrogen is 14.007, basically 14, and oxygen is 16. So if we go back, now let's try to figure out the molar mass of this. First, magnesium. That's what I say it was, 32.4. 20, oh, well, that's wrong. 24.3. Close enough. 24.3. Plus, now it gets a little dicey. We have NO3, but we have 2 of them. So what you can do is simply say 2 times, in parentheses, the molar mass of NO3, which is nitrogen's 14 plus 3 times oxygen. Oxygen is 16. And then you close with parentheses. So if you put that into the calculator correctly with the parentheses, it will give you the right answer. If you forget to put parentheses here, it won't. Because it'll do 2 times 14 plus 3 times 16. Instead of 2 times 14 plus 3 plus 16. Or times 16. So does that make sense? You're basically figuring out how many atoms of each element are in the formula, and then just simply adding those masses up.
Yes.
Good? All right, cool. So it doesn't get much more difficult than this. These are the most difficult examples. So if you figure them out, you should be pretty good. And just to solve this, we have 24.3 plus 2 times 14 plus 3 times 16. 148.3. 148.3 G per mol. That's the unit, grams per mole. Okay, cool. So now, what can this? So using that skill, we're going to use that skill in a bit. So another way to think of these chemical reactions, now we're going to try to tie in the mole to chemical reactions. So we talked about chemical reactions first, then we talked about the mole. Now we're going to put two together. So the way we can read a chemical equation, going back to this one we talked about before, is we can say that not only two molecules, excuse me, I thought I had a hiccup, but I didn't. So we can't only say that two molecules of H2 are reacted with one molecule of O2 to create two H2O. We can say that 2 moles of H2 plus 1 mole of O2 reacts to produce 2 moles of H2O. So that's this sentence right here. Very important. So 2 moles of H2 react with 1 mole of O2 to yield or to produce 2 moles of H2O. That's the way to read it, because that sentence means a lot to me. If you were on a bench top and you had H2 and O2 and a scale, well, even though they're gases, you can't really weigh them that easy, but let's say you could, and you had that on a scale and a scale, and I told you, I want to do this reaction. You can do it instead of trying to figure out, all right, how am I gonna get 2 molecules of H2 and one of O2? You don't need that. You just need the number of moles. So I'm like, all right, let's calculate the mass of 2 moles of H2, put that on the scale and weigh it out. Then we'll calculate the mass of 1 mole of O2, and then put that on the scale and we'll weigh it out. And then we'll mix both of them together. Once we do that, we get our product. So this mole quantity and this relationship between moles is important because it tells us how much we need to actually, or how much we need on a macro level in terms of grams to actually complete the reaction. Does that make sense? Okay, cool. So it's kind of scaling it up to what we can see. Now, follow-up question. So how many grams, and these are the kind of questions that I'm going to be asking next, using these relationships, is how many grams of H2O is produced from 4 moles of O2? That's a loaded question. Okay, so let's think about this. We have to use our brain a little bit, even though it might be a little early. So how many grams of H2O is produced from 4 moles of O2? Now this balanced equation tells us that 1 mole of O2 creates 2 moles of H2O. If 1 mole of O2 is responsible for 2 moles of H2O, then how many moles of H2O is formed from 4 moles of O2?
2.
Not 2.
8.
8. Good job, Devin. So there's a 1-to-2 ratio, meaning there's 1 mole of O2 that makes 2 moles of H2O. So if this was 4 moles of O2, like the question's suggesting, then this one, the H2O, to keep that ratio the same, would have to be 8. So there'd be 8 moles of H2O. Does that make sense?
How did you get 8?
Okay. So if you have, so in the equation, you understand the ratio that 1 mole of O2 makes 2 moles of H2O, right?
Yes.
Okay. The question that we're asking for this one, follow up, is saying that how many grams of H2O, so don't worry about grams yet, just say how much H2O is produced from 4 moles of O2. So instead of 1 mole of O2 making 2 moles of H2O, we're being asked for 4 moles of O2. And how much does that make? So if 1 makes 2, then 4 will make 8. That's where you get the 8 from. So does that make sense?
Yeah. it does.
Okay. All right. Cool. Cool. So once you do a lot of practice with this, it'll make more sense. All right. So the answer is 8 moles, right? But that's not the question. So the question is, how many grams of H2O is produced? So we figure out that 8 moles of H2O is produced from 4 moles of O2. Now we have to figure out how many grams is that. So here's what we can do. Here's what you're supposed. So there's going to be a chart later on to show you how to do these calculations. But here's how we're going to do it. First, we figure out the molar mass. All right, so H2O, the molar mass of H2O, if you look at the periodic table, hydrogen is 1, oxygen is 16. So it's going to be 1 times 2 plus 16 equals 18. So H2O is 18 grams per mole. Does that make sense? Okay, so 18 grams per mole. So now, this means that for every 1 mole, there is 18 grams. So write that down. So 18 grams over 1 mole. Now, we're looking for the amount of grams, not in 1 mole, because we know that's 18, but the amount of grams in 8 moles. So if 1 mole has 18, what would you do to figure out how many grams 8 moles has?
18 over 8.
I heard multiply by 8, then I heard 18 over 8. So you wouldn't divide by 8. You'd multiply by 8. Because if you put 8 moles up here, moles will cancel out, and you get 18 times 8 grams. So it makes sense. If you have 1 mole is 18 grams, we want 8 moles. It would be 8 times as much. So that's why we do that. You'd have 18 times 8, which is 144. 144 grams of H2O. Okay, does that make sense? Give you a second to write. All right. So it can get a little bit more difficult too. So we'll take it one step further. Here's another question that could be asked. How many grams of water are produced from 20 grams of H2? Okay. So 20 grams of H2. You notice how these chemical reactions, they don't say anything about grams. They are just talking about moles. 2 moles reacts with 1 mole to create 2 moles of this. Nothing about grams. So in these kind of equations, in these kind of questions, anytime you see grams, convert it to moles. That makes it a lot easier for everybody. Whenever you write, you can write that down in your notes. Whenever you see grams, convert it to moles. That'll help you. So if you have 20 grams of H2, how many moles is that? All right. We can figure out the same way that we did for this. So H2, the molar mass of H2 is 2. It's 2 grams per mole. And Kaylee, good job. So that's the answer at the end. That's the answer for the moles. So you have 2 grams per mole of H2. So, right, because you add 1 plus 1. All right. So if you have 20 grams of that sample, and you know that 2 grams of it is each mole, how many moles are in 20? So you do the same thing. We have 2 grams per mole. Or we could write it this way. Hold on. 2 grams divided by 1 mole times, we have 20 grams. So we have 1 mole, or sorry, X moles. Oh, no, we could just divide. Well, really, we're dividing by 20. We're doing like moles over 20 grams. So what we're doing is we're taking the 2, basically the way I'm going to teach you how to think about it is you're dividing by 20. 2 divided by 20, or sorry, the other way around. You're 20 divided by 2. So you're basically, scratch all this. Hold on. So what you're doing is you have your 20 grams and you know that there is, you're trying to convert this to moles. So you know that 1 mole is equal to 2 grams. Grams will cancel out, and you get 20 divided by 2 equals 10 moles. So we have a small molar mass, which is 2, and our big sample, which is 20. So we do 20 divided by 2 gives us how many sections of 20 can we section off to make them moles. And we can split 20 10 times to make little 2 gram per mole samples. So that's how you do that. Is any questions on that? I have a better way of making it more simple. So the question is now, to follow up on this to finish it off, how many grams of water are produced from 20 grams? So now we know that 20 grams of H2 is 10 moles. So the question is how many grams of water? Now, if we look at the equation, we see that 2 moles of H2 produce 2 moles of water. So that's a 2 to 2 ratio, basically a 1 to 1 ratio, meaning for every amount of H2, you have the same amount in moles of H2O. So if you have 10 moles of H2O, or sorry, of H2, you're going to have 10 moles of H2O. And then what you can do is take that 10 moles and multiply it by the molar mass of H2O to figure out what is the mass in grams of water produced. So the mass of H2O is 18, like we saw before. So that's going to equal 180 grams. So does that make sense?
So the final answer is 180 grams.
Yes, because it's asking for how many grams of water is produced. So we have to compare the H2 and the H2O in the equation. And you know that there's 10 moles of H2. That means there must be 10 moles of H2O produced. And then you multiply that by the molar mass of H2O to get 180. All right, so if you don't want to remember how I did those calculations, or if you want an easy way to remember them, here's how. Now this is the relationship between grams, molar mass, and also particles. Or sorry, grams, moles, molar mass, particles, Avogadro's number. This is a key thing right here. So if you want to write this down in your notebook, I highly suggest it. Now I'll do some examples. Let's say we have 3 times 10 to the 23rd molecules of HCl. And we want to figure out how many grams that is. So we want to go all the way over to grams. How would we do that? We could do that by following this chart. So let's look at the arrows. Particles, atoms, or molecules to moles. So the only way we can get from molecules to grams is we have to go through moles. There's no way we can go from particles just to mass. We have to go through moles. So first, take the number of molecules and figure out how many moles that is. And the way to do that is dividing by Avogadro's number. And the reason is because Avogadro's number is the number of molecules or atoms in 1 mole. So whatever number you're dividing by it, dividing by it, that means it's that certain fraction of a mole. So in this case, it's 3 times 10 to the 23rd. This means that it's going to be half a mole. So if we divide 3 times 10 to the 23rd by 6 times 10 to the 23rd, you get approximately 0.5 moles. Does that make sense of how I got 0.5?
Yeah.
Yeah? All right. Okay. So next, we have the number of moles, 0.5 moles. The question's asking for, if we have that number of molecules of HCl, how many grams? All right. So we need to go from moles to grams. So we'll follow this green. Going from moles to grams. What we're going to do is ignore this. Ignore these things. Just focus on what I wrote. I wrote up here, multiply by the molar mass. That's exactly what you do. You multiply by molar mass. Molar mass of what? The molar mass of HCl, which is in the question. So what we're going to do is we're taking that 0.5 moles and we're multiplying it by the molar mass of HCl. So we can go back to our table. Hydrogen is 1. Cl is 35.45. So we're doing 0.5 times 35.45. No, there's 36.45 because the hydrogen is 1. HCl 1 plus 35.45 equals 36.45. Okay, so then we multiply this together and we get whatever half of 36 is, and that's going to be 18. So it'd be around 18.2. 18.225 to be exact. Now it'd be grams. Okay. Is there any questions on how I did that? And there should be, because that's kind of complicated.
Oh, sorry. Can you explain, because I'm seeing different processes, so I don't know which one is which.
So, okay, yeah, there's two. So this is all one process. It all follows this chart,
Okay.
but there's different steps of it.
Okay.
So if you know this chart pretty well, it should be pretty easy. Now, in this case, I went from the molecules to the grams. So I went all the way. I did just to show you the different ways that this works. But I went from particles to grams. So basically what you're doing, go from particles to moles. You have to do that first in order to get from moles to grams. You can't just go from particles to grams. So we're dividing by Avogadro's number because we're trying to see what percentage of a mole is that number of particles that's given. In our case, the given is 3 times 10 to the 23rd. So we're dividing that by Avogadro, and we get 0.5. Once we get 0.5, we're at moles, 0.5. Then we want to go to grams. So we're going to multiply by the molar mass. It's right here. So multiply by molar mass. So we take the molar mass of whatever compound we're dealing with, and we multiply it by the number of moles, which is 0.5 times 36.45, and you get the number of grams, which is 18. So it's a stepwise process. And you can go backwards too. So if you had the grams and I was asking you for the moles, you would divide by the molar mass and basically just do the opposite. You would divide by molar mass and then you would multiply by Avogadro's number. So hopefully that makes a little bit of sense. With examples that we're going to do in the next slide, it'll make more sense, hopefully. And we'll go over them together. So I'm trying to think other things. Yeah, so another thing is it's really good to think about this intelligently. Because you might make mistakes on the calculator or you add the wrong number. I'm not sure. But if you are multiplying, let's say you're trying to go from moles to molecules. If you go from moles to molecules, is your number going to get bigger or smaller?
Bigger.
Good, a lot bigger. Good. Just by knowing that information, is your number getting bigger or smaller? That will tell you whether to multiply or divide. So moles is usually, in this case, it's 0.5. In other cases, maybe it's 1, it's 2, it's 3. It's kind of small. You should never have 10 to the 23rd moles. Then you know you're probably wrong. So if you have just a small number of moles and you're trying to go, or any number of moles, you're trying to go to particles, the particle number will always be a lot bigger, on the order of 10 to the 22nd, 3rd, 4th, 5th, whatever. So that tells you that you need to multiply by Avogadro's number. Same thing going the other way. If you want to go from grams to moles, is grams bigger or smaller than moles? Somebody can answer that.
Smaller?
So you had a 50-50 shot, and unfortunately, that is not the correct answer. So it's okay. So thank you for participating. So now that's a good point. Now the mass is always going to be bigger than the moles because, well, I mean, for hydrogen, they're about the same, right? Like you have 1 mole is 1 gram, but everything else is going to be bigger. 1 mole of carbon is 12 grams. So even 0.5 moles of carbon is 6 grams. So the idea here is that mass is bigger, but mass is never going to be 10 to the 23rd. It's never going to be that big. So if you want to go from mass to moles, mass is bigger than moles. So you're going to have to divide. And you divide by the molar mass. That's a bad circle, but you get my point. So using this chart, you should be able to figure out certain things. So now I'm going to give you guys some practice. And hint, these are similar to possible test questions. So here's what I'm going to do. I'll give you guys until it's 9:11. I'll give you till 9:16. I'll give you like five or 6 minutes to do these. And I'll leave this up here. You can do them in your notebook or whatever scrap paper you have. And I'll leave this. And where it says here, where it says m equals n over times m, don't worry about that formula for now. Just think, if you're going from moles to mass, you're multiplying by molar mass. If you're going from mass in grams to moles, you're dividing. It's a percent. You're dividing by mm, which is molar mass. Okay, I'll give you guys until 9:20. Give you guys full 8 minutes. 5 more minutes, and then we'll go over these together. A couple more minutes. You probably hear my cat meowing in the background. She wants attention. She has food, so I don't know what she's complaining about. Anyway, let's get started. All right, so first one. 1.204 times 10 to 24 molecules of water equals how many moles of water? So if we're going from molecules to moles, which is here, particles and molecules, all the way to moles, we're dividing by Avogadro's number. So if you divide 12 or 1.204 times 10 to the 24 divided by 6 times 10 to the 23rd What did you approximately get?
I got 2.0.
Good. Should be just 2. Yeah, around 2 moles. Good. Okay, does that make sense? Any questions?
Yeah, what do you do with the if it's 10 to the 24 over 10 to the 23? What do you do with the exponents again? Is
Okay, good idea. A good question. So, basically, so the reason why it's 10 to 24 is because this is proper scientific notation. Now, technically, it's the same thing as 12 times 10 to the 23rd if we move the decimal over. But since this is proper scientific notation, what we do is if we divide 1.2 by 6, what do we get? We get 0.2. I think we get 0.2. So 1.2 divided by 6 is 0.2. And then we do the same thing like we did before. 10 to the 23rd divided by 10 to the 24 divided by 10 to the 23rd is 10 to the 1. So because you subtract the exponents. That would mean this would be 10 to the 1. So 0.2 times 10 is 2. That make sense?
Yeah.
Yeah, or you could, since you're going to have a calculator on the exam, you could just put it in a calculator and you're fine. But when you do put it in a calculator, make sure you put parentheses around everything just to be safe. Because what will happen is if you don't put parentheses around 6 times 10 to the 23rd in the denominator, it will do divided by 6, and then it'll move the 23rd to up here in the numerator. And your answer will be something crazy like 10 to the 47th, which you can't have that. That means you did it wrong. So yeah, just beware of that. So it'll be 2 moles of water for the answer. Next one, 3 moles of HCl is equal to how many moles or how many molecules of HCl? Okay, so we have moles. Moles is 3. Multiply by Avogadro's number to get to particles, and you get 3 times 6.02 10 to the 23rd. Or what do you get? What do you get?
18.06.
Boom, nice. So 18.06 times 10 to the 23rd, or if you want proper notation, 1.8 times 10 to the 24. 06. Sure.
Can you show the process on how that was the answer?
So you multiply 3 by Avogadro's number.
Oh, okay. Thank you.
Okay. Next one, 34 grams of KF is how many moles of KF? So what we would do is figure out the molar mass of KF. So KF equals potassium. We look in the periodic table. Potassium is 39.098. We can make it 39.1. That's fine. 39.1 plus the molar mass of fluorine. Fluorine is 18.998 or simply just 19. And this is going to equal 58. 58 grams per mole. So this is how many grams are in 1 mole of KF. If our sample is 34 grams, we're going from grams to moles. So we look at the chart, we go from grams to moles. The number is getting smaller, so we have to divide by our molar mass. So if we divide 34 by our molar mass, we get 34 divided by 58, which is equal to what? Anybody? Nobody did it. That's not good.
0.58.
Good, I think. Let me see. 34 divided by 58. Yep. Well, technically 0.59 if you round it's 0.586, but we can make that 0.59. But good job. That's how many moles it would be. Okay. As long as everybody understands it, it's okay. So if you don't do these practice problems, you're not going to understand really what I'm doing unless you do them yourself beforehand. I gave you a good amount of time to do that. So just try your best to we'll be having examples. And oh, it's okay, Juan, don't worry about it. All right, next one. So we have 2.3 moles of Na2SO4 to grams. So we want to go from moles to grams. We're multiplying by the molar mass, multiplying by molar mass. So first, to multiply by the molar mass, we need to figure it out. So Na2SO4, we're going to add 2 NAs, 1 S, and 4 O's. So 2 sodiums. Sodium is 22.99. So basically 23. Where's the... There it is. All right. So we have 23 times 2 plus sulfur. Sulfur is right here, and that's 32.06. So that one, it's not good to round. So we'll leave it as 32.06. Plus 4 oxygens. Oxygen is 16. So 4 times 16. And I think Na2SO4 is 122 or something. But let me just double check. Oh, 142. 142 grams per mole. So that's the molar mass of Na2SO4. The question's asking for if basically our molar mass is telling us 1 mole is 142. 2.3 moles is what? So we would multiply the number of moles by the molar mass to get the grams of the sample. So 142 times 2.3, and what did you get for that? Anybody do it?
Uh, 326.6.
Okay, great. Thank you. So 326.6 grams. Okay, that sums it up. Are there any questions on these?
Can you repeat how you did the last one, please?
Okay. Do you understand how I got the molar mass?
I'm not sure at the moment.
Okay. What we did was we took Na2SO4 and we looked at the periodic table for Na, which is sodium. And we saw that the molar mass was 23, about, if we round up. So there's 2 of them. So 23 times 2. We did the same thing for sulfur. Sulfur is 32.06. And the same thing for oxygen, and there's 4 of them. So it'd be plus 4 times 1. Plus 4 times 16. And that would be 142 grams per mole. That's the molar mass of Na2SO4. From there, we can take a look at the chart. Now, we see that we're going from moles to grams. The number is going up. So we're going to multiply by something. And that something is the molar mass. So we're doing 2.3 times the molar mass of 142 gives us 326.6 by following the chart. Does that make sense?
Yes, so it's 2.3 times 142.
Yes.
Okay, great. Thank you so much.
Okay, cool. So let's move on. We're almost done. A couple more slides. Now, solutions. So this is a very important skill. You're going to have more examples on this in a bit, after we're done. But solutions. So a solution is really a way of further quantifying these types of things, these molecules and these compounds. We're going to be using in solutions a large amount of liquid, whether it be milliliters and liters worth, to do certain chemical reactions. And you can have either a dilute or a concentrated solution. And you've probably heard of those words before, dilute and concentrated. And we can calculate a solution's concentration based on something called molarity. Now, which we'll get to in the next slide. But dilute, if something is dilute, that means it has a very low concentration, meaning a low molarity, or there's not many particles per volume of the liquid. So if you dilute your drink, for example, you're going to put more, let's say you water it down or something, you put more water in it. That's not really good for alcoholic beverages. It doesn't really taste good. But let's say you have a hard alcohol and you put in Coke, you put in a soda with it, right? That dilutes the drink. It makes it more tolerable and the less doesn't sting as much. But that's one example of diluting that we see all the time. Maybe you guys are most of you guys are under 21, but many of your parents probably do that. But yeah, the PG-13 example would be like orange juice. You could dilute that too. You could dilute anything. But yeah. Okay, then you have concentrated solutions. So concentrated are very concentrated, for lack of better words, which means you have a large amount of the particle, or what we call the solute. So meaning the particle that's in the solution, you have a large amount of it in a small volume. So if you have, for example, in the lab, we use hydrochloric acid a lot. If you have dilute hydrochloric acid, you can get it on your skin. It might burn a little bit, but not really. Let's say 0.1 molarity, 0.1 molarity. It's not too much. If you have concentrated hydrochloric acid, 10 molar, 10 molarity, 15 molarity, what that means is it's so volatile that if you get it on your glove, it might actually burn through your glove, and it fumes. It's really bad for you. So you have to be very careful in the lab. So we can accurately determine these solution concentrations with the following formula. And it's a pretty easy formula. And this formula will be given on the exam. It's called the molarity formula. And the way you calculate the molarity, which is the moles per liter of solution. So if you have a certain moles of solute, so let's say your alcoholic beverages, moles of alcohol per liter of your alcoholic beverage. If you want to dilute that and add water or add a soda, it would increase the liters. So the liters would increase, but the moles would stay the same because you're not adding more alcohol to diluting a drink. You're just leaving the same amount of alcohol, but spreading it along more volume. So if you increase the denominator and leave the numerator constant, this molarity number will go down. This is how dilutions are done. The volume increases, the molarity decreases because the moles stay the same. So that's a dilution. And this is the concentration formula. And Juan, good idea. Be classy and add ice. Ice is another way of diluting it too, because technically ice is water, so it'll dilute the drink as well. But if you leave the ice too long, it melts and then the drink doesn't taste as good. But you're right, classy, and you can add ice. Okay. So now knowing this, here's an example. If you have 1 mole of a substance in 0.5 liters, then the molarity is 1 mole divided by 0.5 liters, or 2 molar. So that's the kind of thing we'll be doing here. So does that formula make sense? Would you be able to do calculations with that, you think? Because we're going to do some examples now. Okay, cool. There's one more nuance to this. It might not be as straightforward as this example. I might give you grams. Then you'd have to convert it to moles with what we just learned. Or I might give you molecules. In that case, you'd have to convert it to moles like we just learned to get the moles into this equation. Additionally, the volume that I give you might not be in liters. It might be in milliliters. In that case, you'd have to convert. So there's these other factors that are involved. We're kind of combining these concepts that are very important. So we're going to be doing a bunch of examples. And actually what we're going to do is, I changed my mind. We're going to be doing a worksheet at the end. So, gotcha. All right. Anyway, before we do that, this is the last slide we're going to do. We're going to go over these together. We'll go over the first one together. And then the last 3 you can do by yourself. And then we'll go over them. All right. So the first one. What is the molarity of 0.5 liters of solution? Or 0.5 liter solution of 34 grams of NH3. All right, so it's asking for molarity. So we're looking for the molarity formula. M equals the moles over the liters. Now, what do we have? We have a 0.5 liter solution. Okay, so we have liters, 0.5 liters. And then we have 34 grams of NH3. Now, the numerator tells us moles, not grams. But we know how to go from moles to gram, or sorry, from grams to moles. So if we find out the molar mass of NH3, which is 14 for nitrogen, plus 3 times 1 for hydrogens, this equals 17 grams per mole of NH3. We're doing this in order to find the number of moles of NH3 that's in 34 grams of NH3. So if we look back at our chart, if we're going from mass to moles, we are dividing by the molar mass. So we're taking this 34 grams that we have, 34 grams, and we're dividing it by the molar mass of NH3. So 34 divided by 17 equals 2, which is, that's a good whole number. So we have 2 moles of NH3. This 2 moles goes in the molarity. And you have 2 divided by 0.5, which is 4 molar NH3. So that would be the answer. So any questions on that? No? All right. So I'm going to give you I'll give you 4 minutes or so, 9:41, to finish these next 3. So you can go ahead and do those, but then we'll go over them. And then I'll give you a little worksheet and we'll split into breakout rooms. I just wanted to make the worksheet. That was the quickest worksheet I ever made. I just spliced some questions from different sources. Anyway, all right, let's do these. What is the volume in liters required to prepare 3 molar solution containing 2 moles of a substance? It's not really being specific on which substance, but it doesn't matter. So we have 3 molar, sorry, that means the concentration, equals the moles divided by the liters. So we're not given the liters, we're just given the 2 moles. So we divide by liters, and that's going to be X liters. So we basically cross multiply, or however you want to solve for X. And the number of liters we get is 2 over 3, or 0.67 liters. So that would be the answer there. Okay, next one. What is the molarity M of a 2-liter solution that contains of 3.2 moles of strontium hydroxide? This one's pretty easy. So what we do is we take the molarity formula and we just divide the 2. We're given both moles and liters. So we do 3.20 moles divided by 2 liters, and we get, was that 1.6? Yeah, 1.6 big M, 1.6 molarity. Good job. And then the last one, what is the molarity of 30 milliliters of a 0.25 mole solution of HI? So anyone want to explain to me what we do?
Yeah, convert milliliters to liters first.
Good. Now, how do you do that? How would you want to do that?
Dividing by 30 by 1,000.
Perfect. Good. Some people do it differently. What you can do is, my favorite is just dividing it by 1,000. Or you can just move the decimal place over 3 times. So 1, 2, 3, and you get 0.030. That would be for liters. So what we can do is take that number. Sorry, I have a lack of room. 0.25 moles divided by 0.030 liters. And what do you get for that answer?